Hi, I'm Hyungjin Chung. I will be presenting our work, Parallel Diffusion Models of Operator and Image for Blind Inverse Problems, a joint work with Chungsul, Sehee, and Professor Ye. In this work, we are interested in solving blind inverse problems, where we only have the corrupted measurement y, and we wish to recover the clean x. Here, we do not know the exact degradation operation that generated the measurement. A representative case would be the case of blind deblurring, where we do not know the blur kernel. In order to jointly estimate both the image and the blur kernel, we devise a diffusion model-based method dubbed blind DPS, short for blind diffusion posterior sampling. Specifically, we construct two parallel diffusion paths, which will be run jointly to produce both the estimate of the image and the kernel. As the reverse diffusion progresses, we see the following coarse-to-fine progression of both the image and the kernel. As a result, we show that we can solve blind deblurring even in cases where we have extremely high corrupted measurement, thanks to the power of diffusion models. We also show that our method is fully general and can be also extended to more complex blind inverse problems such as imaging through turbulence. Our method is built on diffusion models. Diffusion model is a class of generative model that generates data by iterative denoising. The training of such generative process boils down to training a residual denoiser that learns to denoise an image given noisy realizations of different magnitudes. Usually, the trainable network is set to a U-net with a time-dependent conditioning scheme. On the other hand, we are interested in solving inverse problems in this work, where the aim is to recover the clean image x from the noisy corrupted measurement y. Due to the ill-posedness of the problem, there exist infinitely many solutions that are feasible, and hence it is our job to properly incorporate the prior of the data distribution in order to achieve a good estimate. Now, when we know the imaging operator A phi precisely, the problem is called non-blind, and it is easier to estimate x. A more challenging problem arises when we also do not know what the imaging system is, which are called blind inverse problems. Over the recent years, there has been continuous growth in the interest in using diffusion models as generative priors to solve inverse problems in imaging, thanks to their amazing sample quality and modularity of the inference procedure. In essence, you can leverage a pre-trained denoiser as is and slightly modify the inference procedure to achieve a posterior sample that matches the measurement condition. However, it should be noted that all method focused on the case where the forward operator is exactly known. This scheme can also be interpreted as a method of Bayesian inference, as the denoiser in the diffusion model can also be thought of as the score function, which is the gradient of the log prior. Hence, we can achieve posterior sampling by incorporating the data likelihood into the denoising scheme and plugging in the gradient of the log posterior into the reverse diffusion, or the reverse SDE that governs the diffusion process. Diffusion posterior sampling is a representative work that solves inverse problems with diffusion models. Here, the time-dependent log posterior can be decomposed into the score function and the time-dependent likelihood. Here, the score function can be approximated with an unconditional diffusion model. However, as the likelihood term is intractable due to the dependence on t, in DPS they devise a method to approximate this term, which is simply given by plugging in the Tweedy denoised estimate of xt into the likelihood function. When this is done, now the term becomes tractable and can be flexibly applied to different measurement conditions, showing applicability to diverse problems. However, coming back to the DPS formulation, we can see that the method assumes perfect knowledge of the forward operator A. What if we do not know the operator A, as in the blind inverse problem setting? Here, we consider the case where we know the functional form of the operator, but do not know the parameters to simplify our argument. A representative case would be the case of blind deblurring, where we know that the measurement is generated by a convolution, but do not know which kernel generated the blur. In the Bayesian sense, the posterior distribution can be represented as the product of three constituents: the likelihood, the image prior, and the kernel prior, and these two factor out because of a dependency. In this work, we aim to model both of the priors with the diffusion prior, due to the recently proven amazing capacity of these priors. In order to do so, we can train the diffusion models independently. Now, in order to achieve posterior sampling, we first construct two independent reverse SDEs. If we were to run these two processes, we would get prior samples independently from px and pk. To actually achieve posterior sampling, we plug in the likelihood term. However, similar to DPS, this term is again intractable. In order to make the terms tractable, we devise an approximation method that replaces xt and kt with the Tweedy denoised estimates x0 hat and k0 hat, and formally show that the approximation error is well controlled. Let us inspect what blind DPS is proposing visually. We start from the usual DPS, where we have a single diffusion model that models the prior distribution of the images. Here, the update step involves simulating the measurement with the denoised estimate of the image x0 hat, and taking a gradient step to minimize the residual between the simulated measurement and the real measurement. Now in blind DPS, we have an additional diffusion path, and we estimate both the image and the kernel via Tweedy denoising, and apply the gradient steps to both the image path and the kernel path. We find that for kernels, it is often more beneficial to include some amount of sparsity-inducing priors to the process of stabilization. Running the reverse diffusion steps, we see that our method yields the following coarse-to-discrete evolution of both the image and the kernel, yielding high-fidelity reconstructions. Note that while we focused our presentation for the case of image deblurring, our method is fully general in that it can be applied to more complex blind inverse problems such as imaging through turbulence, where there is an additional tilt induced by some vector field. In essence, our method can be applied to all cases where the probabilistic graph is constructed as follows, where each component are conditionally independent on the measurement. With blind DPS, we are able to achieve state-of-the-art reconstruction quality, while other prior arts struggle in the extreme blurring conditions. Moreover, the ablation study against using the diffusion model, but fixing the kernel prior to be the uniform prior, we see that using the diffusion prior for the kernel greatly improves the performance of the kernel estimation. Similar to blind deblurring, we see again the high-quality reconstructions also for imaging through turbulence. Thank you for listening. If you're interested in, please check out the paper in the code.